Show me your boards. I see. Let's see. Some similarities, some differences. I'm going to take a look up here. So we've got, hold that up there, B greater than D equals C greater than A. If your board matches that board, you can put it down. B, D, C, A. You guys had something close, didn't you? You're close? Okay. All right. I don't know that this is right, though, but let's go through it and make sure that we all understand the physics that embodies this. How did you approach this problem? What did you do? Yeah.
Some of the forces is the same thing as the net force. So
yep.
You can use the formula F equals ma in order to find the A. And then you rearrange the equation so that you can equal A, so it's F net over M equals A. And then you solve for each one and then put them in order.
And just compare.
Yep.
Does that kind of match what we did? Yeah. Yeah. You guys know this. We've been dealing with this for a whole unit, right? This was unit 3 right here. This is Newton's first and second law. We are going to move in today to unit 4. So pull out some notes and we're going to write down the big idea from unit 4. So go ahead, you can erase your boards for right now. We are going to do another ranking test in a little bit, so go ahead and leave it there. Get out your notes. You can write unit 4 really big. A new book just for unit 4? Friends, unit 4 has 3 standards in it. We're going to get one of them done before winter break. We'll do the other 2 and put it all together after the new year. Okay? So, you've got notes out? We kind of get in funny habits sometimes in this class. Like we'll give you a bunch of papers to fill in. But today is a notes day. So you've got your own paper out. We're going to write down the big deal. Are you ready? Here it comes. Have you seen this before? Yeah, you totally have. This is the big deal for Unit 4 too, but we're just going to repackage it. How many of you have ever gone into the store of your choice that carries your toothpaste? You know what I'm talking about? So whether that's Hy-Vee or Target or wherever you get your toothpaste, wherever that is. And you know that you're looking for the box with the green letters and the sparkles on the side or whatever, right? You walk in and then you're looking at and you just like stare at the toothpaste section and you can't find your box. You know what I'm talking about? Like whatever brand it is, Colgate or Crest or whatever fancy pants brand, whatever you get, okay? You stare at the boxes, you can't find your box, and then after a while you realize, there it is, it's been looking at you the whole time, but they just put it in a new box. You know what I'm talking about? Yeah. Same great formula, new look. Remember that? Yeah, that's happening maybe with your orange juice or whatever. Like, I'm sure that at some point you have purchased something where you've been like, wait, this is not the same container, right? Soda companies like to do that a lot, right? They have it's the same liquid inside that's eating your insides and doing all kinds of fun things to you, right? But it just has a new wrapper on it. That's what we're doing today. New wrapper. Same great physics, new look. Are you ready? So we're going to start with this, the same formula, same stuff. Okay, I'm just going to change a couple things. And you guys, I'm not even teaching any new physics. We're just kind of putting stuff together. You've seen this acceleration thing before. What does acceleration mean? What does it mean to accelerate? Yeah. Change in velocity, right? It's going to speed up, slow down, change direction, something like that. Yeah, so we could say that acceleration really just means change in velocity. So instead of A, I'm just going to write down the change in velocity over time. Is that okay? No big deal. And I'm going to leave the rest of it exactly as it was. F net over M. Okay. Well, that's cool. Now, the next step I'm going to take is the step just to make people not scared. Because I know that sometimes people get scared of denominators. Oh my gosh, they're so scary because, they're down. I don't know. You're looking at me like I'm nuts, but I'm telling you, like I used to teach middle school and like lower high school math, and I will tell you, friends, they are scared of denominators. So we're just going to get rid of the denominators. Can we do that? Yeah, it's like like checking under the bed to make sure the monsters aren't there? That's all we're doing. So I'm just going to multiply by m on both sides and multiply by t on both sides. Is that allowed?
Yeah.
Sure it is. Just doing algebra. Just doing algebra to make everybody happy. So we're going to multiply by t on both sides because that t will cancel. And then we're going to multiply by m on both sides to make that m cancel. And so it's a little bit messy, but it's really just the same thing. So I'm just going to put another little line here. Same great physics, new look. So we've got m delta v is equal to F net times T. Okay. Same physics, new look. Put a big box around that. This one's a big deal right here. This thing right here, such a big deal that they give it a name. What? They give it a name. Like, this is a big deal thing. And it's not just Newton's first and second law. Newton's first and second law, as you've been taught it since you were a wee tot, was this, right? But I'm going to tell you a secret. Shh. If you look in the books that Isaac Newton wrote, when he revolutionized, big air quotes, revolutionized physics, when he wrote what we now call Newton's first and second law, he actually wrote it like this. That's exciting, right? And it has a new name. Here's the name. Are you ready? It's a really fancy name. Here it comes. It's called the Impulse-Momentum Theorem. And you know it's got to be a big deal if it's called the Impulse-Momentum Theorem, right? A theorem's a big deal. That's it right there. Okay? So there are two words. The only one, or three words, the only one you've heard is theorem. So probably impulse and momentum are things that we need to define, right? Impulse lives on one side, momentum lives on the other side. We're going to do momentum first. So here it comes. We're going to talk about momentum. I'm going to put a big box around this thing right here. This thing right here represents, well, that delta means what? Change, right? So this represents the change in momentum of an object or a system. Okay? Momentum is marked with the letter P. So change in momentum is delta P, and delta P is equal to m delta V. So now we're going to use our great Monday morning minds to do some logical reasoning here. If delta P equals m delta V, what do you think that P equals? If the change in momentum equals the mass times the change in velocity, what do you think that momentum equals? Talk to your table mates. Are you ready? What did you come up with? What did you come up with? Yeah. Well, that is true. That is true that delta P is equal to F net times T. I'm trying to ask. I think maybe it's even like too simple of a question. Let me write it out. What I'm really talking about here. Let me write out what I'm really talking about. I'm saying that delta P is really like final momentum minus initial momentum. Yeah, change in is equal to the mass times the final velocity minus the initial velocity. Is that okay? That's just literally what change in means. Okay. So that means that, well, we could like, what is that? Distribute mv final minus mv initial is equal to pf minus pi. So hey, the final momentum is equal to what? The mass times the final velocity. Okay. This new quantity, new day, new unit, new quantity, this idea of momentum It's just two values multiplied together, okay? Mass times velocity. That's all it is. A lot of times people get really, really worked up about what momentum is or something like that. Literally, it's just the mass of an object times its velocity. That's it. That's it. Okay? Okay? It's a quantity that describes mass times velocity. So now we're going to play a little game. Are you ready? Okay? The game, it's like a game show. I'm going to work on this over winter break and see if I can pitch it to a network. Okay? The game is which has more momentum. Are you ready? Okay? So you're going to vote. And I'm trying to figure out how we should do this voting because I think it'd be good to do it individually. So this is what we're going to do. So there's an A and a B, choice A and choice B. If you think that it's A, you need to stand up. Okay? And if you think that it's B, you need to get out of your chair and squat down. Yes, you do. Because it's Monday and we got this. Okay, so nobody's sitting in their chairs. Because if you're sitting in your chair, that means you're abstaining and then you need to make a choice. Okay? So I'm going to read the question. Then I'm going to say 1, 2, 3, go. Remember, A is standing up and B is doing what? Squatting down. Okay? We're going to get the blood flowing. It's going to be great. Here it goes. Which has more momentum? I need like a theme song to go with this, but I haven't written it yet. So you guys have to wait. I'll work on that over winter break. Maybe we'll have like a revisit to this later. Oops. Woo! We'll start here. All right. Situation 1. Which has more momentum? A runner traveling at 2.5 meters per second or a runner traveling at 12.5 meters per second? Same runner. I'm going to say 1, 2, 3, and then you need to either stand up or squat down. Which has more momentum? Have you got it in your head? 1, 2, 3, go. Which has more momentum? Look at you guys, 100% participation. That makes my heart so happy. Why does runner B have more momentum? The teachers, they're waiting. More velocity, same mass, more velocity. Remember, we said, come on, silly thing. We said that momentum is mass times velocity. Bigger velocity, bigger momentum. You guys are great. If only I had like a cash prize to give you. I really don't. I'm still, like I said, I'm still working on this. Are you ready for round 2? Here it comes. Round 2. A boulder rolling at 3 meters per second or a marble rolling at 3 meters per second? So remember, A is get up, B is get down. Ready? 1, 2, 3, go. Look at y'all. You're all standing. Why are you standing? Has more what? Mass. Yeah. Momentum is mass times velocity. The bigger the mass, the bigger momentum. 2 for 2. You ready for round 3?
Wait, they're both A.
What's that?
They're both A.
Oh, they are. Oops. So everybody stood up. I'm assuming that nobody was really voting for that. So I don't know if I fixed it on the other one. So if I didn't, the one on the left is going to be A and the one on the right is going to be B. Fair enough? All right, here we go. Round 3. This is the final round. Double or nothing. You're going to put all your winnings on the line. Here it comes. A running mouse or an elephant standing still? A running mouse or an elephant standing still? Ready? 1, 2, 3, go. Everybody votes. Everybody votes.
Yeah.
I see 100% participation. Y'all are standing. Talk to me about why you chose to stand.
For the elephant is happening. So it's velocity, the change of velocity is 0, so just.
Did you guys all catch what he said? The elephant's big, right? I didn't actually tell you the masses of these things, but elephants generally bigger than mice unless there's some sort of interesting genetic mutation, right? We're going to assume that the elephant's really, really big, but remembering in our brains that momentum is equal to mass times velocity, if the velocity is 0, regardless of how big the thing is, the momentum is still what? 0. Okay? I'm going to give you 1 minute to write this all down, to keep that in your brain. If you need to look at all 3 examples, you can, whatever works for you, but get this in your brain so that you know what's going on. There are the 3 examples so you can see them kind of. Whoa, can't get it that small. There you go. Write down what you need to on your paper right now. How do you keep track of which one's bigger, which one's smaller? Because we're going to do a ranking task in just a moment. Got to make sure we're ready to go. Got it? Get that graphite moving. Write it down, friends. Write it down, write it down. Next thing's coming. All right, friends, are you ready? Okay. A ranking task for you. So after break, we're gonna do some labs with our. Do you remember that cart that we had with the pulley? They can actually interact with each other, and it's really super fun. We're gonna do a lab kind of like this. But right now, I just want you to take a look. We've got these carts with spring plungers that are running into fixed barriers. The carts are identical, but carrying different loads, so they have different masses. Okay? The velocity of the cart just before and just after the impact is given. This ranking task asks you to rank the magnitude of the change of the momentum of these carts. Okay? I'm going to give you a couple minutes to work on this. Actually, I'm going to give you 1 minute to work by yourself, and then I'll let you discuss. Does that sound okay? So 1 minute of quiet. You work with your brain. It should be quiet for a moment, and then I'll let you talk. Shh. All right, friends. Show me your boards. Let's take a look. I see boards from almost all the tables. Do you guys have a board? Nothing written on it yet. Okay. I'm seeing a lot of. Did you say something yet? Not yet. Almost. So close, so close. I see a lot of all the same. But as you know, I don't want to just know the answer. I want to know why, right? Or how you know. So can you talk me through? I don't even know that's the right answer. Now let's take a look. How are you going to figure this out? Or how did you figure this out? Let's do table, somebody at table 15, 16. What did you guys do?
We take the change in velocity, so 25 minus the
Okay. Multiply by the mass? Is that what y'all did? So if we do that, because that seems to make sense, because they're asking for the change in momentum, right? Change in momentum equals mass times change in velocity. A lot of what we're doing right now, friends, is just getting that word into our vocabulary and getting that idea into our brains. So the mass stays the same before and after the collision. And so you just do change in velocity. So let's do it just to make sure that we're all good. So final minus initial, right? M, V final minus V initial. So we got a final velocity of 0 minus 4. So 0 minus 4 gives me a change in velocity of negative 4 and a mass of 10. Is this right? Are we doing okay? Yeah? So this is negative 40. Okay, and so the next one, then we've got a final velocity of negative 1 minus 3. So it's going to be negative 4 times 10 gives me negative 40. Yeah? Yeah? Negative 2 minus 2 is negative 4 times 10. Negative 3 minus 5 gives you a change of velocity of how big? Negative 8, right? Times 5, also. How are we doing? Everybody happy? Sweet. I want to make sure everybody's got it because we got to keep cruising. So we've got now, if we go back to our lovely equation, the one that Newton got rich on, right? This is it. This is it right here. We've done half of it. Now, I told you that it's called the Impulse-Momentum theorem. And I told you that this is the momentum part. So using our logical reasoning then, friends, what does this have to be? It does. So get your notes out. If they're not out, if your pencil's not ready to go, here we go. We got to do impulse. So this is the impulse part. It's right over here. Doop, 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 doop. Impulse. So momentum is a word that and a concept that we use in physics a lot, so much so that it's given a letter. The letter is P, right? Why? Because momentum starts with a P, right? I mean, it seems to. Yeah. Impulse is also a concept that we use a lot in physics. The letter that's associated with it doesn't show up very often, though. I'm going to tell you because I know that there are some among us that like to have things organized and like to have letters that are associated with things. The letter that goes with impulse, if you care, if you want to know, is the letter J. But I don't even know if that exists in your book. Like, I had to look it up because I didn't know, because usually they just call it impulse. And they say that impulse is M delta V, okay? So the game here is that in order to change the momentum of something, you have to apply a force, right? If we're going to change the velocity of an object with mass, we have to apply a force. We know that that's true. But the game, and the reason that we care about this, is that change can happen in lots of different ways, okay? There are many ways to change the momentum of an object. Okay? You have to apply a force, and that force is going to have to be applied over a time, but there are lots of different ways to do that. Okay? And we're going to talk about one of them right now. So I walked into the back room while you guys were working on your ranking task, and I got myself an egg. And no, it's not hard-boiled, by the way. I didn't hard-boil it last night. The thing that I used to hard-boil eggs makes them like brown on one side, so this is a raw egg. Okay? So I can apply a force to this egg over time, and I can give it momentum. You with me then? Okay? I apply a force over time, I give it some momentum, and then I can aim it at the board, and I can throw it, and what would happen if it hit the board?
I don't know.
It would what? It would go splat. So talk to me, friends, from a physics perspective. If I take this egg and I throw it, so I give it some momentum, so now it's got momentum, it's flying through the air, and it hits the board, does it change momentum? It would stop, right? Which means that it would change its velocity, and it has mass. So if it's changing velocity, it's changing momentum. And if it's changing momentum, that's because there's a force acting on it over time. Yeah? You're like, do it. So we're going to do it. But, right? So what I need, I want you two guys to come here for a second. Mostly because you're tall. And do I have any softball players in here? Anybody? Baseball? Baseball? Okay. All right. So hold on just a second, Hunter. I'll get you started. I'll have you come up in a minute. All right. You guys are tall. That's why I fired you. Because I'm not. Okay. So what we're gonna do? I haven't done this for a really long time. Never in this room. This is the first time today in this room. Are you ready? Okay. Don't chew it up. Stand. I'm gonna hold this. Corey, come here. I'm gonna hold this side over here. And then you'll clean it up. Just get out of your way. All right. And so you're going to hold this kind of here. Okay? You don't want that so far back that it's going to hit the wall. You know what I'm saying? So maybe just a little bit like this. You're doing okay? All right. So friends, yeah. So I have to tell you like the full disclosure story. So I haven't done this since I've been at Liberty High School. I was just talking to Mrs. Hughes about this a little while ago, and she used to teach the 9th grade Foundations of Science class back at West High School, and they did this because they did this concept, and she did this demo, okay? And she was an athlete, but she was a volleyball player, and she apparently, when she threw this egg, released really high And they did this, like they had it up like this and it was beautiful. And where did the egg go? It went over, right? So any like potential scholarship opportunities are on the line today. You understand what I'm saying?
Yep.
So we're gonna hold this up high because I've not seen him play baseball. I don't know how good of a aim he has. Are you a pitcher or what do you do?
Pitcher.
Okay. So this is the strike zone.
Yep.
Okay, right here, not up there. We're not trying to walk anybody.
Yep.
Okay? No intentional walking. All right. Now, are you gonna have any aim? Like, do you want to do it that way, or do you want to like? We could have Natalie move, and you could say, I don't know, what's gonna be the best for you. What do you think? You don't care. He's like, now, I do want you to throw it kind of hard, like, because I don't want it, like, here's the thing. It's not just like bounce, right? It was like, woo, like that's not very exciting. These guys would all be very disappointed. If you just, because I can do that, right? Woo! It didn't break, did you see? Oh my gosh, physics works! No, that's not what I want. So I should throw it with a little bit of velocity, okay? Like, I don't know how fast you throw on the mound. Like, I don't want to, you know what I'm saying? Okay. All right, are you guys ready? Yes. Have you guys seen them play baseball? Pretty good? Connor, you look a little skeptical back there.
I struck you out.
Oh! Ooh! A little bit identical. All right, I'm getting out of the way. Hold on, I gotta be back here so I can watch. So, and you guys are good. You're gonna hold it up, right?
That'd be awesome.
All right.
She's just playing.
Let's make physics work, you guys.
Let me do it.
Well, you're not just standing there for nothing, so I guess yeah. That was pretty hard. And did it break? Go check. Max is speaking with some authority. Should he try it one more time? So, question: if and not when, but if he had thrown it against the wall, would it have broken?
Yes.
Indeed, he would have. Yeah. Okay. Now, don't bounce it off the table. Okay, like I'm getting nervous. I'm not gonna lie. All right. Woo! Let's go physics. Go. Make it happen. Still okay? Is it still okay? Did it make it?
Yeah.
Thank you. Awesome. If the baseball thing doesn't work out, you just want to be a professional
Egg thrower.
egg thrower, we will make that happen. All right. So, friends, it made a sound that I heard from back there. It made a sound, and that sound would imply that it hit with some velocity, yeah? Which means that it had some momentum, and that momentum changed. How did it change? What happened? Why did it change? It changed momentum because of why? What happened to it? It hit the sheet. And the sheet did what? It stopped it by applying a force. Let me try that again. By applying a force. There. And it applied a force over some time. So the reason that I told them not to hold the sheet way up here is because then it really would have just hit the board. You with me there? Yeah, and if we did that, and I kind of want to, but I'm not going to because I don't want to clean it up. If I did that, the force of the board on the egg would happen really, really, really fast. Are you with me? So that means at the time, because remember we're saying that impulse, this J, is equal to force times time. And really, that's just the change in momentum. Change in momentum, Impulse-Pmomentum theorem, right? If the force, or excuse me, if the time is really, 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 really little, then that means the force is going to be really, 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 really what? Big? Does that make sense? To get some sort of momentum, let me rewrite that. Let me say that in a different way. To get the same momentum, same change in momentum, we can have a couple different situations. If the egg hits the board, how long does it take for that egg to break? For that egg to change its momentum? Oh. How is the time very big or very small? Very small, right? Small time. Big force. But luckily for us, I remembered, I saw the note last night that said, bring this sheet. Because what did the sheet do? What did the sheet do for our change in momentum? Did y'all watch the sheet?
Mm-hmm.
Yeah? Haley got a video of the sheet, right? If you watch that in slow-mo, did the sheet stay very, very stiff and still? No. What did it do, friends? It moved, right? Which meant that the force of the sheet on the egg lasted a longer amount of time. That means that we had a big amount of time, which means what about the force? It was a much smaller force. And in which case do we have a safe, happy, uncracked egg? Small time, big force, or big time, small force? Which one is it? Big time, small force, happy egg, right? Big time plus small force equals uncracked egg. Tomorrow we're gonna talk a little bit about other things that help do this, right? But instead of for eggs, help humans, right? Can you think of anything in a car that helps this happen in case of an emergency, in case of a crash? Your airbags, right? They allow you to slow down over more time, which means that what happens to your body? You absorb the force, a smaller force, right? Which means you have an uncracked skull, uncracked, better likelihood of survival, right? Moral of the story here, friends, is that the Impulse-Momentum theorem saves lives. Yes, it does. The Impulse-Momentum theorem saves lives. I want to give you a couple practice problems to work on here. We've got, let's see here, bam. Here's one. This is kind of not quite as exciting as the egg. I apologize for that. But here's the situation. We've got a 50 kilogram mass, okay, kind of a substantial mass, sitting on a frictionless surface. It says it should be a constant force. Typo, I apologize for that. A constant force pushes on the mass for 2 seconds until it reaches a velocity of 3 meters per second. Okay? I think sitting at rest, maybe. Okay. Question says, what is the initial momentum? What is the final momentum? And then figure out the force and the impulse. I think you can do this. So I'm going to let you work for a couple of minutes. I'm going to let you talk to your table mates, figure this out, and then on your board, I want you to split your board into 4 quadrants, A, B, C, D, and put your answers to those questions on your board once you've got them. Sound good? Make it happen. All right, let me see your boards up here. 2 out of 4. 2 out of 4. You guys are like putting it together, then you're like, oh, 100% there. All right, let me see. So it looks like we're kind of there, but maybe not quite. Is that true? So let's go ahead and go through it, shall we? Let's take a look. Let's start at the beginning. A 50 kilogram mass is sitting at rest on a frictionless surface. What is the initial momentum? How do you find momentum, friends? Momentum is mass times velocity. And if we're talking about the beginning, the initial momentum is related to the initial velocity. The initial velocity is? So what's the initial momentum? 0. Hey, what are the units of this thing? Anybody know? Nope. Got to figure it out, right? What are the units of M? Kilograms. What are the units of V? Meters per second. What are the units of momentum? Anybody want to guess? Kilogram, meter per second. Bam, you got it. Easy peasy, no problem. Okay? We'll come up with a nicer way in just a second, but let's do final momentum. So final momentum, PF is equal to mv final. So you got your 50 kilograms, and it says it reaches a velocity of 3 meters per second. So 50 times 3, I can do that in my head. I hope. What you got? 150. 150 what? Not newtons. Kilogram, meter per second, right? That's it. You got it. All right. Now it gets maybe a little ugly, maybe not. Some people are like, I got this part, no problem. What was the force acting on the mass? How in the world do you figure that out? That's a good question, Miss Gray. I don't know. How did you approach this? Try it.
Could you do F net T equals M changing V, and then plug in 150 for M changing V, and then you know the times, and you just do T F net or 2 F net, and then divide by 2.
So let's talk about this. So hold on, I'm gonna actually write this as delta P. Let's talk through what he just said, because that was a lot of stuff that just happened. Do you guys agree with this statement in green down here? For sure you do. What's this thing called? Impulse-Momentum theorem, right? Yeah. You know the change in momentum. What was it? 150 minus 0 gives you 150, right? You do know the time. It says that it takes 2 seconds. So you got 150 kilogram meter per second. You got a 3 seconds. You got F net. Or not 3 seconds, excuse me, 2 seconds. What's 150 divided by 2? Bam. F net equals 75. 75 what? It's a force. Newtons, yeah. So that's B. Or C, excuse me. And then what is the impulse? How do you figure out the impulse, friends? Say it, Emma. You were saying it. Take that times 2. 75 times 2, because it's the net force times the time, which is 150, he says, with a little bit of a yawn. Or, because that's 100% right, I totally agree. Or you can just look at the change in momentum. In either case, what do you get? 150. So we could call it kilogram meter per second, right? That's 100% fine. Or we can look at this and say, hey, what's a force measured in? What's time measured in? Seconds. You can also call this a Newton second. Okay? Newton second and kilogram meter per second squared? Same. Okay? I've got one more thing for you. Are you ready for it? Yes is the right answer. All right. Oh, no, she says. Oh, yes, I say. You got 2 minutes. I want you to do it. I want you to look carefully, guys. You've already done this problem. This was the warm-up problem that you did 40 minutes ago. It's the same thing, but it says now rank the change in momentum. Because if it's over the same amount of time, friends, the change in momentum is the same as the acceleration. Question.
Why is momentum silent?
Because that's how you spell momentum.
The P and
The P is silent.
that's just
Well, you haven't been in physics then.
that's
That's how we spell it. Momentum is spelled with a P for sure. For sure it is. Did you guys get the answer to the question? Do it real quick.
Yeah, we gotta do this. Milo, you ready?
Or just look at your...
No bush, but like bush. Oh.
Hey, physicists, we're not quite done. I do want you to understand this, and I don't want you to turn your brain off. Just because I said you've done it before doesn't mean that I don't want you to engage with it. Identical boxes filled with different objects initially at rest. Rank the change in momentum. Rank the change in momentum. change in momentum equals F times T. How do the times compare, you guys? Same amount of time. So how do you rank the change in momentum? As what gets bigger? What gets bigger? Rank the change in momentum. What are you going to look at? The time is the same in these cases. Write down an answer on your board. You've got just a moment. I want to see it.
Wait, was it DAC? Come on in. Bro, I think it is. Wait, Joel. Joel. That's my answer.
E is the biggest. A and B are the same, and C is the littlest. Have a good day, you guys. If you have not yet taken your test, come see me right